Welcome to Module 5, Part 7. In this section, we are going to study the CMOS inverter and its fabrication. Complementary metal oxide semiconductor is a combination of N-channel and P-channel MOS transistors. So here on the left you can see the N-channel transistor, and to the right you have the P-channel transistors. So both these transistors are fabricated on a single substrate. So this type of devices are particularly useful in digital applications. So this is the circuit diagram over here on the top. You can see there is a PMOS transistor and then there is a NMOS transistor. So the gate terminal of the PMOS transistor is connected to the gate terminal of the NMOS transistor in this particular inverter circuit. Then the drain terminal of the PMOS transistor is connected to the drain terminal of the NMOS transistor, and that is connected to the output. So the gate terminals which are connected of the PMOS and the NMOS are connected to the input. Then the source terminal of the PMOS is connected to the VDD, and the drain source terminal of the NMOS is connected to the ground. So this is the circuit diagram of the inverter. So whenever you give 1 to the input terminal, you get 0 over here, and whenever you give 0 over here, you get 1 over here. So this combination, this type of circuit we are going to fabricate on this particular IC. Now over here we have the NMOS and the PMOS transistor are fabricated on a single substrate. So this part over here is the NMOS transistor part, and this part over here is the PMOS transistor part. The similar way the connections are being done, you can see the NMOS drain and the PMOS drain is interconnected. So similarly over here the NMOS drain and the PMOS drain is interconnected and given to the output. Then the source terminal of the PMOS is connected to VDD. So over here this is the source terminal. The source terminal of the PMOS is connected to VDD, and similarly the source terminal of the NMOS is connected to ground. So you can see the source terminal of the NMOS is connected to ground. So the gate terminals of the PMOS and NMOS are interconnected and given to the input. So here you can see the gate terminal of the PMOS and the gate terminal of the NMOS. The interconnection is not shown over here, but then they are interconnected, and then the input is given to this particular terminal. Now here you can see the circuit diagram of the inverter where the gate terminals are interconnected. So this is the gate terminal over here and the gate terminal over here. This is the PMOS, and over here it is the NMOS, and then we have the source terminal connected to VDD of the PMOS, and source terminal of the NMOS is connected to ground. So remember that PMOS, whenever you provide 0 to the PMOS, to the gate terminal of the PMOS, so this PMOS will be on, and whenever you provide 0 to the NMOS gate terminal, this will be off. So PMOS will turn on only when we give 0 to this terminal. And similarly, so the PMOS, the gate terminal of the PMOS, if it is given 1, so over here if 1 is provided, so to the gate terminal, if 1 input is given, so this PMOS will turn off. So the PMOS will turn off, and similarly if you provide 1 to the gate terminal of the NMOS, so this will turn on. So there is a detailed explanation for this particular procedure as to why PMOS will be on when it is given 0, and NMOS will be off when it is given 0, and PMOS will be on the NMOS will be on when it is provided by 1, and the PMOS will be off when it is provided by 0. So right now we'll just concentrate on the fabrication rather than discussing why what are the operation of the internal circuit. So here remember that if we give 1 over here, so this transistor will be on and this will be off. So what happens is when you give 1, this particular transistor will be on, so there will be flow of current over here. So over here there will be flow of current, whereas this will be an open circuit. Since it is off, it will be an open circuit, so there is no connection between this point and the and this particular output. So it's an open circuit. So whenever you give 1, so n transistor will be on. So the output n transistor will be on. Similarly, what happens when you give 0? So when you provide a 0, so what happens when you provide a 0 over here is, so whenever you give 0 according to this condition, so the PMOS will be on. So when you give 0 over here, the PMOS will be on, so this will be on, and the NMOS will be off. So this will be in the off condition. When this is on, so there is conduction in the PMOS transistor, but whereas this, since it is off, it is an open circuit, so there is no connection between this point and this point. It becomes an open circuit. So what happens is, when you give 0, this will be on, and there will be a conduction. Since the transistor is on, there will be a conduction. So whatever signal you provide over here, so if you give 5 volt, assuming we give 5 volt, which is considered as 1, so 5 volt is considered as 1 digital input, and 0 volt is considered as 0, 1 and 0. So this will be on, and whatever supply we provide will be taken across the output, will be given to the output. It will not flow down like this. So since this is off, there is no flow of current like this, so it will flow through this. So the output V out will be 5 volt. So when it is 5 volt, it is 1. So whenever you give, when V in is 0, V out will be 1. V out will be 1. Similarly, now we will check what happens when you give 1. So when you give 1 at the input side, what happens? So now the second condition is when you give 0. Second condition is when you give 1. Now when you give 1, according to these two conditions over here, the second condition, so the input is 1. So whenever you give this is the first condition, and this is the second condition. So whenever you give 1 over here, the PMOS transistor will be off, so this will be off, and the NMOS transistor will be on. So when this is on, there is conduction path over here, flow of current over, through this, whereas this is off, so there is no path between these two. So this is an open circuit over here. Now when this is on, so whatever output you have will be going to the ground. So whatever output will be pulled down to ground. So when it is pulling down to ground means, so this output will be 0 over here. So whenever you give 1, the input as 1, the output will become 0, since it is pulled down to ground. Since that NMOS transistor is on, it will be pulled down to ground, whereas this will be off. Now one of the important property of this particular circuit is, in either case, either whenever it is 1 or 0, whenever you provide 1 or 0, in either case only one of the transistor will be on. So one particular transistor will be on. Either PMOS will be on. In the first condition you have seen, either PMOS will be on. In the second condition, so only the NMOS will be on. So in either case only one of the transistor will be on. One of the important application of this CMOS inverter is the ultra thin, ultra little power consumption. So since it uses very less power, it is basically used in digital applications such as electronic watches, where you need very little power consumption, or else the battery life will not be good. Then it is also used in the ultra large scale integration, since millions of transistors will be integrated on a single chip, on a single IC. The power consumption of each transistor will matter a lot. So, millions of transistors, if they consume more power, then the power dissipation will increase. So since CMOS inverter consumes very less power, this is very useful in ultra low power applications. So here you could see there are two transistors integrated on a single substrate. PMOS transistor over here, and then next is a NMOS transistor. There is a single big substrate, and then transistors are integrated under certain biasing conditions. So this PNP part and then NPN part, here it is PNP, this is PNP, and over here it is NPN. So under certain biasing conditions, so this causes a large current to flow. When there is a large current flowing through this PNP and this NPN, the problem of latch-up exists. So this is a serious problem in CMOS circuits. The latch-up problem is a serious problem in the CMOS circuits. Now there are several methods which have been used to eliminate this latch-up problem by including the N-type and the P-type tubs separated by a trench isolation. So there are tubs over here. So there will be a tub like this. This is the NP tub and this is the N tub, and then there will be a trench. There will be a trench kind of, the pathway kind of thing over here. So this is one of the method of eliminating this latch-up problem. Then the use of two separate tubs also solves the problem of the latch-up because of the independent control of the threshold voltage in both the transistors. So next we will check the fabrication of this particular transistor, or this particular inverter, by the process of a twin tub. It's called a twin tub process. So we'll go into the detail of this twin tub process. Both NMOS and the PMOS transistors are integrated on a single IC by this particular method, the twin tub process, where you have the N well as well as the P well. The tubs are nothing but the wells. To form these twin wells in a self-aligned fashion, we should first grow the pad oxide on a silicon substrate. Here you can see the silicon substrate. This is the silicon substrate. It's a P substrate, and then we have the epitaxial layer over this P substrate, and then we have the silicon dioxide. So pad oxide has to be grown on the silicon substrate, followed by low pressure chemical vapor deposition of silicon nitride. Over here you can see silicon nitride Si3N4 above the silicon dioxide. Now this silicon nitride stack is covered by the photoresist. Above the silicon nitride, the blue strip is the silicon nitride. Above the silicon nitride, there is a photoresist. Now this photoresist is opened up to form a N well. Reactive ion etching is then used to etch the oxide nitride. So over here there is oxide, and over here there is nitride. So to etch this oxide nitride, reactive ion etching is being used. So this basically, for better understanding, I'll just draw it over here. So this is the entire substrate, P substrate, and then we have the epitaxial layer over this P epitaxy. Then according to the diagram you can see, there is silicon dioxide on the entire surface. Silicon dioxide is grown on the entire surface over here. So this is SiO2, and then we have the silicon nitride on the entire surface. Actually silicon nitride is there on the entire surface. So this is Si3 and N4, silicon nitride. Then we have the photoresist on the entire surface. Over here we have the photoresist. So this is photoresist on the entire surface. So this is the photoresist. Then after that what is done is, so this oxide, only in this part, the oxide, so only in this part the oxide and the silicon nitride and the photoresist is being removed. So reactive ion etching is then used to etch the silicon nitride and the oxide. So if we remove only this part, so this is removed over here. So if we remove only that part, what remains is, so this part, only this part remains, silicon nitride, and then the photoresist remains. So only this part remains in this. So this is the photoresist, this is the silicon nitride, and then you have the SiO2. So this part has been etched off. So that's what it is shown over here in this particular diagram. To form a N well, now N well has to be formed in this particular region. N well has to be formed. So we'll draw this little big, we'll draw the epitaxial layer little big, and then the substrate. So this is the P substrate now, and then you have the epitaxy layer. So this entire thing is the epitaxy layer. Now over here we have to form a N well. So remember, we are fabricating this transistor. We are fabricating the NMOS transistor, and then we are fabricating the PMOS transistor. So first we'll fabricate the PMOS transistor. For the PMOS transistor, the base is the N well. For the NMOS transistor, the base is the P well. So for PMOS, N well is the base, and for NMOS we fabricate the NMOS in the P well. So this is the P substrate, P epitaxy. Then to fabricate the NMOS we need a P well. So here you can see this is the P well, and to fabricate the PMOS we have the N well. So this here you can see we have the N well. So now we are fabricating the PMOS, so we need a N well in this. Now what is done, we have etched off everything over here. The photoresist is etched, silicon dioxide is etched, then silicon nitride is etched. Now using the diffusion method, so phosphorus is being diffused in this particular region. So phosphorus is being diffused in this particular region to form a N well. So here you can see phosphorus is diffused in this particular region to form the N well. So here you can see the N well. So fast diffusion is used to drive the dopants deep into the substrate to form the N well. So when the phosphorus dopants are diffused in this particular region, so a N well will be formed like this. So now this is a N well. We'll remove this epitaxy. We have the epitaxy over here. Now we have diffused phosphorus, and we have the N well ready. So this is now my N well. In this I can fabricate PMOS transistor. So in this I can fabricate the PMOS transistor. Now to fabricate the NMOS transistor we need a P well. So the similar process is being followed, where we etch off this particular part. Now silicon dioxide is grown on the entire surface. Again silicon dioxide is grown on the entire surface, and then the nitride is grown on the entire surface. The photoresist is grown on the entire surface, so that while the dopants are diffused in this particular region, it will not affect the N well. Now the dopants are being diffused. So phosphorus dopants are being diffused to form N well. Now after that the entire silicon dioxide, silicon nitride and photoresist are developed on the entire surface, and then later using the process of reactive ion etching, only this particular region is being removed. Resist is as it is, then silicon nitride is kept as it is. So only this part is open now. So when we diffuse the boron dopants in this particular region, now we diffuse boron dopants to form the P well. To form the N well, phosphorus dopants were used. Now to form the P well, boron diffused are being used. So this etching part is done to diffuse this boron. Now over here, even though boron dopants are diffused like this, it will be diffused on the entire surface, not just the region where it is open. It will be diffused on the entire surface. Even though it is diffused in this particular region, it will not go into this, and it will not damage this P epitaxial layer or the N well. So since there is a photoresist and silicon nitride and silicon dioxide, it will not enter in this particular region, whereas over here it will just enter and then form a P well in this particular region. So we have the P well due to the boron dopants, and due to the phosphorus dopants we have the N well. So now we have the P well to fabricate the NMOS transistor, we have the N well to fabricate the PMOS transistor. So here you can see all the boron impurities are doped to form the P channel. Now after this the photoresist is removed and the wafer with the pattern silicon nitride oxide. So now after this the photoresist is being removed, and the wafer with the pattern silicon oxide stack is subjected to wet oxidation to selectively grow a field oxide. The nitride layer blocks oxidation of the silicon substrate in this particular region. So here we can see the phosphorus and the boron impurities are diffused into the substrate to a well depth of typically a micron, driven by diffusion at very high temperature of about 1000 degrees Celsius for several hours. After this diffusion process, silicon nitride oxide stack, or the silicon nitride and the silicon dioxide stack, and the tank oxide are etched away. Since this tank oxide consumes silicon from the substrate, etching it off leads to step in the silicon substrate delineate. Next, after this step, we form the isolation regions or the field transistors that will guarantee us there is no electrical crosstalk between the adjacent transistors due to interconnection. Now a stack of silicon dioxide and silicon nitride is patterned over this particular substrate using photolithography process, and then it is subjected to the boron channel stop implantation between the twin wells. So here boron is fed between these twin wells. This increases the accepted doping and thus increases the threshold voltage of the P well between the N transistors. The boron will compensate the donor doping of the N well side and will reduce the threshold in the N well between the P channel transistors. After the channel stop implant, the photoresist is being removed and the wafer will be patterned with silicon nitride oxide stack. Now after this, the polysilicon is being placed on the surface where you need the gate terminal. Right at the center, at this point we need the polysilicon, and over here we need the polysilicon which acts as a gate terminal. Now the final process will be in a similar way to implant the P diffusion over here to form the gate terminal. So in the in this P well we have the N diffusion, that is the phosphorus, and in the N well we have the P diffusion, that is the boron, to form the source, drain and the source terminal. Over here the drain and the source terminal. Polysilicon is already done. Polysilicon is placed in the beginning. It's already placed in the beginning. So the same process is being used to diffuse the N impurities and the P impurities to form the source and drain terminal, and then this is the gate terminal over here. At the center we have the gate terminal. So this is the fabrication of your twin tub process. Thank you.